Robotic duct cleaning. Air side balancing and performance testing. Animations and graphics by Arvind Avan. Subject matter expert, trainer, and content writer. Contents. 1. Objectives. 2. OSHRI guidance. 3. Tools required for robotic duct cleaning. 4. Duct cleaning procedure. 5. Air balancing. 6. Performance testing of air handler. Objectives. In an air conditioning system, the air is transported by ducts. Over a period of time, several impurities collect on the inside surfaces of the ducts. Some of the impurities are: 1. Dust and dirt. Dust and dirt can accumulate in air conditioning ducts, particularly if the air filter is not regularly cleaned or replaced. This will result in poor IAQ and increase in energy consumption. 2. Allergens. Allergens such as pollen, pet dander, and dust mites can also accumulate in air conditioning ducts. This can cause allergies and respiratory issues for people who are sensitive to these allergens. Definitions. Pet dander. It is tiny flakes of skin shed by animals, such as dogs, cats, birds, and rodents, as well as proteins found in their saliva and urine. Dust mites. These are microscopic organisms that thrive in warm and humid environments, such as bedding, carpets, and upholstered furniture. 3. Mold and bacteria. Moisture can build up in air conditioning ducts, providing a perfect breeding ground for mold and bacteria. This can lead to unpleasant odors, and can also be a health hazard for people who are sensitive to these substances. 4. Insects and rodents. Insects and rodents can also find their way into air conditioning ducts, particularly if there are gaps or cracks in the ductwork. This can introduce unpleasant odors and can also be a health hazard. 5. Chemicals and pollutants. Chemicals and pollutants from cleaning products, personal care products, and other sources. This can lead to poor air quality and may also be a health hazard. Regular cleaning of the air conditioning ducts will: A. Prevent the buildup of these impurities, and can help to maintain a healthy indoor environment. B. Prevent excessive energy billing. OSHRI, guidance on acceptable levels of indoor air pollutants. IAQ in an air-conditioned building refers to the quality of the indoor air that occupants breathe in a building that is equipped with air conditioning, AC, systems. Good IAQ in an air-conditioned building means that the air is free from harmful pollutants, odors, and irritants, and that it is comfortable and conducive to occupant health and well-being. OSHRI provides guidance on acceptable levels of indoor air pollutants to help ensure good indoor air quality, IAQ, for building occupants. Here are some details on the guidance provided by OSHRI for some common indoor air pollutants. 1. Carbon dioxide, CO2. OSHRI recommends that the concentration of CO2 in indoor air not exceed 1,000 parts per million, ppm, above outdoor levels. The outdoor concentration of CO2 is typically around 400 ppm, so this means that indoor levels should not exceed 1,400 ppm. Higher levels of CO2 can cause drowsiness, headaches, and reduced cognitive function. 2. Volatile organic compounds, VOCs. OSHRI recommends that the total concentration of VOCs in indoor air not exceed 500 micrograms per cubic meter. This includes both individual VOCs and the total concentration of all VOCs. Exposure to high levels of VOCs can cause eye, nose, and throat irritation, as well as headaches, dizziness, and fatigue. 3. Particulate matter, PM. OSHRI provides guidance on acceptable levels of PM, based on the size of the particles. For example, the concentration of PM with a diameter of 2.5 micrometers or smaller, PM 2.5, should not exceed 15 micrograms per cubic meter. The concentration of larger particles, PM10, should not exceed 50 micrograms per cubic meter. Exposure to high levels of PM can cause respiratory problems, such as asthma and bronchitis. The negative effects of dirty AC ducts on IAQ can be significant. For example, the accumulation of dirt and debris can restrict airflow, which can cause the HVAC system to work harder and less efficiently. This can lead to higher energy bills and increased wear and tear on the system. To address the issue of dirty AC ducts and maintain good IAQ, it is important to have the ducts cleaned regularly by a qualified professional. This involves using specialized equipment to remove the dirt and debris from the ducts without damaging the HVAC system. By keeping the AC ducts clean, a building can maintain good IAQ and ensure the health and comfort of its occupants. Tools required for robotic duct cleaning. Robotic cleaning of AC ducts requires specialized equipment and tools to effectively clean and sanitize the ductwork. Some of the common tools required for robotic cleaning of AC ducts are: 1. Robotic cleaning system. A specialized robotic cleaning system designed for cleaning AC ducts. It should be able to navigate through the ductwork and use different cleaning tools and technique to remove dirt and debris from the ducts. The robotic duct cleaner typically includes a high-powered vacuum system to suck up dirt and debris, along with a variety of brushes and scrubbers to remove built-up grime and dust. The robotic vehicle can be remotely controlled by an operator, or can navigate autonomously using pre-programmed cleaning paths. One advantage of using a robotic duct cleaner is that it can access hard-to-reach areas of the ductwork that may be difficult or impossible to clean with traditional methods. 2. Inspection camera and display. A duct inspection camera and display system is a specialized tool that allows technicians to visually inspect the interior of air ducts for signs of dirt, debris, damage, or other issues. The camera is typically attached to a long, flexible cable that can be snaked through the ductwork to capture high-resolution images of the ducts. The camera is typically equipped with high-powered LED lights to illuminate the interior of the ducts, and may also include a zoom function to allow for detailed inspection of specific areas. The images captured by the camera are transmitted in real time to a display screen, which allows the technician to view the interior of the ducts and identify any issues that may need to be addressed. By detecting and addressing issues such as dirt buildup, leaks, or damage, technicians can help to ensure that the HVAC system operates efficiently and effectively, while also improving indoor air quality and reducing the risk of health problems associated with poor air quality. 3. Brushing tools. Different types of brushing tools are used for removing dust and debris from the ducts. These tools can be used to scrub the walls of the ducts, to remove stubborn debris and buildup. Brushing tools are specialized cleaning tools designed to remove dirt, debris, and other contaminants from the inside of air ducts. These tools typically consist of a series of brushes or bristles that can be attached to a flexible cable or rod and inserted into the ductwork. There are many different types of brushing tools available, each designed for specific types of ductwork and cleaning applications. Some common examples include: A. Round duct brushes. These brushes are designed for use in circular or rounded ductwork. They can be made from a variety of materials, including nylon, wire, and polypropylene, and may be attached to a flexible rod or cable for easy maneuverability. B. Flat duct brushes. These brushes are designed for use in rectangular or flat ductwork. They may be attached to a rigid frame or a flexible rod, and can be made from a variety of materials, including nylon, wire, and polypropylene. 4. Rotary brush systems. These systems typically consist of a motorized brush head that can be attached to a flexible cable or rod and inserted into the ductwork. The brush head spins rapidly, allowing it to remove dirt and debris from the ducts. 5. Air whip systems. These systems use a high-pressure air compressor to blast dirt and debris from the ductwork. The air is directed through a series of flexible hoses and nozzles, allowing it to reach deep into the ducts, and dislodge stubborn contaminants. The type of brushing tool that is best for a particular application will depend on factors such as the type of ductwork, the level of contamination, and the accessibility of the ducts. 6. Vacuum systems. A vacuum system is an essential component of air duct cleaning equipment, used to remove dirt, debris, and other contaminants from the inside of air ducts. The vacuum system consists of a powerful suction unit that creates negative pressure in the ductwork, allowing it to draw in and capture dirt and debris. In the context of AC duct cleaning, a vacuum system is used in conjunction with specialized cleaning tools, such as brushes and air whips, to dislodge and remove contaminants from the ducts. The cleaning tools are inserted into the ductwork, and the vacuum system is used to capture the dislodged debris and prevent it from escaping into the indoor environment. There are many different types of vacuum systems used in air duct cleaning, ranging from portable units to large, truck-mounted systems. Portable systems are typically used for smaller cleaning jobs or in situations where access to the ductwork is limited, while larger truck-mounted systems are used for more extensive cleaning projects. The efficiency of the vacuum system is an important factor in the effectiveness of air duct cleaning. A high-powered vacuum system is necessary to create the negative pressure required to dislodge and capture debris from the ductwork. Additionally, the vacuum system must be properly sealed and equipped with filters to prevent the dislodged debris from escaping back into the indoor environment. 7. Control system. The control system is a crucial component that enables the operator to control the movement and operation of the robot. The control system typically consists of software and a control interface that allows the operator to remotely control the robot's movements and operations. Duct cleaning procedure. 1. Preparation. A. Remove the last supply air diffuser at the fag end of the duct. B. Remove the VFD. 2. Inspection. Inspecting ducts for robotic cleaning typically involves using a camera system fixed to a robotic vehicle to visually inspect the interior of the ducts and identify any areas that may require cleaning. Here are the general steps involved in inspecting ducts for robotic cleaning. A. The robotic cleaning system should also be set up and ready to use. B. Place the robot inside the duct through the diffuser opening. C. View the monitor to see if there is any obstructions that may interfere with the camera's view, such as debris or furniture. D. Maneuver the robot through the ducts to get a clear view of the interior. E. Identify areas that require cleaning. These may include areas with visible debris buildup, mold growth, or other issues that could affect the air quality of the building. F. Measure the airflow through all the terminals. G. Measure the performance in TR of the air handler. 3. Cleaning plan. Based on the inspection results, a cleaning plan is developed. This may involve focusing on specific areas of the ducts or using different cleaning techniques depending on the type and severity of the buildup. 4. Robotic cleaning. Once the cleaning plan is developed, the robotic cleaning system is used to clean the identified areas. The system typically uses brushes, air jets, or other tools to remove debris from the ducts. 5. Final inspection. Once the cleaning is complete, a final inspection is conducted to ensure that all areas have been cleaned properly. 6. Air balancing. Balance the supply air from all the terminals, according to the designed requirements. 7. Performance testing of the air handler. Carry out the performance test of the air handler, to see if it is as per the designed requirements. If not, inspect the entire AC system to identify the causes. Air balancing. Determining air quantities from terminals. Steps. 1. The building must be in normal occupational mode, in design conditions. 2. Ensure that all the dampers and VCDs are open 100% and then operate the plant. 3. Record the ambient climate conditions and room conditions. 4. Take the measurements of the grills and diffusers. 5. Take at least 3 velocity readings at the terminal. Now use the formula given below to get the air quantity at the terminal. Q equals VA. Where Q equals CFM of air at the terminal. V equals velocity of air at the terminal. A equals cross-sectional area of the terminal. Now, adjust volume control dampers, VCD, of all grill and diffuser to open 30%. Starting from the farthest grill/diffuser, adjust the VCD to get the design air quantity from each grill/diffuser. Performance testing of air handler. Steps. 1. Determine the CFM. For this, take an anemometer. 2. Measure the velocity across the face of cooling coil. The unit is FPM. 3. Take at least 6 readings. Then determine the average reading. 4. Take measurement of the coil face in foot. 5. Calculate the area of coil face in square foot. CFM equals velocity multiplied by area. The formula to determine the capacity of an air handler is TR equals 4.5 multiplied by CFM multiplied by delta enthalpy, ER minus ES, divided by 12,000. ER equals enthalpy of return air. ES equals enthalpy of supply air. 1. Now determine the enthalpy. For this, take a sling psychrometer. 2. Measure the following temperatures of the AHU. A. Supply air wet bulb temperature. B. Return air wet bulb temperature. 3. Take a psychrometric chart to find the enthalpy. Below is an example. Assume supply air WB 50 degree F. Return air WB 60 degree F. Return air enthalpy is 26.6 BTU. Supply air enthalpy is 20.5 BTU. Performance of AHU, example. 1. Use enthalpy from the psychrometric chart. Enthalpy return equals 26.6 BTU and enthalpy supply equals 20.5 BTU. 2. Assume coil face velocity as 500 fpm. 3. Assume coil face area equals 20 square foot. 4. CFM equals FPM multiplied by area. Equals 500 multiplied by 20. Equals 10,000. TR equals 4.5 multiplied by CFM multiplied by delta enthalpy divided by 12,000. TR equals 4.5 multiplied by 10,000 multiplied by 26.6 minus 20.5 divided by 12,000. TR equals 22.9. Disclaimer. The information contained in this tutorial has been obtained from very reliable sources, extracts from the internet and personal experiences of the author. The author disclaims all warranties to the accuracy, completeness, or adequacy of such information. The author shall have no liability for errors, omissions, inadequacies in the information contained herein and interpretations thereof. The author and all those who assisted in preparing this tutorial shall not be responsible for loss of any kind, whatsoever, sustained by any person who relies on this material. All graphics, animations, and communication methodology in this tutorial is copyrighted. No parts of this tutorial may be reproduced, stored, or distributed in any form or by any means either on paper or electronic media, unless authorized by the author. The author. The author, Arvind Dhawan, is a mechanical engineer with specialization in air conditioning with over 45 years experience in air conditioning and utility domain. Currently, he is a subject matter expert and certified lead trainer, Level 6 with Electronics Sector Skills Council of India, ESSCI, under the Ministry of Skill Development and Entrepreneurship Government of India, and a visiting faculty with ISHRI. he has contributed to the following: Handbook for Technicians by Ishri. Multi-Skill Technician Handbook by Care, Voltas. Trainers PPT, FTAC for ESSCI. App Contents FTAC for ESSCI. Revamping and refurbishments of the course materials for Ishri. Several courses on multimedia platform available online on https://sbgblv.com. End of the tutorial. Explore our 100% animated, 100% voiceover in English and Hindi, 100% industry aligned, 100% made in India, with creative graphics in 17 multimedia courses, in a wide range of HVAC topics and home appliances. No Google stuff. Contact us, world leaders in multimedia contents and trainings, on https://sbgblv.com, or mail to info@skolenberg.com.